Hi, welcome to the presentation of the paper titled Online Knowledge Distillation for Multitask Learning. I am Geethu M and this paper is co-authored by Vishal Agarwal and Bjorn Stenger. We are from Rakuten Institute of Technology. This paper deals with the problem of multitask learning in pixel-wise computer vision tasks. Multitask learning is a process of learning multiple tasks simultaneously by a single network. Generally, it has a shared backbone and task-specific heads. Multitask networks help in simultaneous inference of multiple tasks but suffers from negative transfer, where the performance improvement in one task leads to the performance degradation of another task. There are several techniques proposed to mitigate negative transfer. Task weighting techniques compute weights for each task, and a weighted loss is used to train the network. These techniques mitigate negative transfer to an extent. Another efficient technique is to use knowledge distillation for multitask learning. This method requires two steps for training, one for training single task network and the second for training the multitask network with knowledge distillation from the features of the models trained in the first step. Building upon the idea of offline knowledge distillation, we propose online knowledge distillation for multitask learning, where single and multitask networks are learned simultaneously. Thus, the training process of single task networks are mimicked in the multitask network. For n tasks, the proposed architecture consists of n single task networks and a multitask network. Although the training is performed simultaneously, the inference is performed only with the multitask network. We use vision transformers, specifically VIT tiny architecture, as the encoder. We also use transformer layers for task-specific heads. We propose two components for online knowledge distillation by which the knowledge of single-task networks are distilled to the multitask network. The first component of online knowledge distillation is termed as adaptive feature distillation, or AFD. This loss performs a weighted alignment of single-task features with multitask features. The degree of alignment of the single-task features of each task towards the MTL features is determined by a learnable parameter omega, which is learned along with the network parameters. The second component is termed online task weighting, or OTW, where we compute weights for task-specific loss functions based on the loss values of multitask and single-task network at that time step. Higher weights are given to tasks for which multitask loss is larger than the corresponding single task loss at that time step. The overall loss function is a combination of the AFD loss function, task-specific single task losses, and OTW-weighted multitask losses. The performance of an MTL network is good only when it works well for all tasks, and we use the metric delta for this purpose. A larger value of delta indicates a larger improvement over the baseline. Here are some results of our method compared to some existing methods on NYU dataset and VIT tiny as our underlying model. It is seen that our method performs the best with an increase of 6.22% of delta value. Similarly, for Cityscapes dataset, our method performs the best with an increase of 9.19% of delta value when compared to the baseline. There are several ablation studies reported in the paper. I quote the most important study here. The biggest contributors as per our study are online knowledge distillation or simultaneous training of models, OTW and AFD. Thank you for watching.